So last time we talked about the field axioms, and we introduced several things. One is called the additive identity, right? Additive identity. One is called the additive inverse. And we also introduced for the multiplication, we also introduced the multiplicative identity and the multiplicative inverse. Then for the additive identity, which is denoted by 0, we say this additive identity is unique, right? We also proved it's unique, and we also proved that the 0 times anything equals 0, right? And if A times B equals 0, and A equals 0 or B equals 0, this is another result we often use. And we also proved that the additive inverse is also unique. Okay, the additive inverse can be described by this symbol, not B, but we use negative A to denote this is the additive inverse. So A plus negative A would be equal to 0, right? So by this one additive inverse, then we can define the difference of this. Yeah, we also can define a new operation which is called the subtraction. Okay, A minus B means the A plus the additive inverse of B. Okay, so now we want to continue. We want to talk about something about the multiplicative inverse, okay, or multiplicative identity. So I have postponed our homework to next Monday. Okay, you can find your homework in your week 2 folder in your Blackboard. Okay, I just moved to that one because the homework should be finished after today's class. Okay, so we have no homework due this Wednesday, but next Monday you will have some homework due. Okay, so now let's look at the next one, which is the thing you needed to prove by yourself. This is the, let me see, this is the 4. This is the 4. So the next one would be 5. Five says the multiplicative for any A, the multiplicative identity is unique. So in other words, 1 is unique. There's no other numbers, okay? So the idea is, suppose you have another 1 prime, you needed to prove that this 1 prime is the multiplicative identity. You need to show that this 1 prime is actually equal to 1, the one we already have. Okay, so this is the basic idea, like we did in the for the uniqueness of the additive identity. You use the similar way. Okay, the only difference is one is the addition, the other one is the multiplication. You can just change the addition to the multiplication. That's it. Okay. Then 6, we want to prove that the multiplicative inverse is unique. Multiplicative inverse is unique. Okay, so let's look at here is the we use the B, okay, B to denote the multiplicative inverse. So we prove, suppose, prove. Okay. Suppose the multiplicative inverse B, okay, we use B. This is B. Suppose B prime is the multiplicative inverse of A. Inverse of A, of number A. A is any real number, okay? A is any real number. In other words, A times B prime should be equal to 1, right? This is the definition for the multiplicative inverse. So A times B prime equals 1. So the next thing is we need to show that B prime is equal to the B. B is the one we already denoted as the multiplicative inverse of A, right? So we need to show that. How do we do that? So let's start from B prime. Okay, I give you time to write down. Is that okay? I can continue. Yes. Okay, so B prime, we start from B prime. So B prime is equal to 1 times B prime, right? No problem. 1 is the multiplicative identity, right? Identity times anything equals that number. This is the definition for the multiplicative identity, 1. Then we also know that for any number A times its multiplicative inverse would be equal to 1, right? A times B should be equal to 1. So we replace 1 with A times B times B prime. A is any number, right? And we know that the multiplicative inverse from the axiom we have, the multiplicative inverse is denoted by B. So A times B equals B times A equals 1. This is what we already know, right? In the field field axioms, you can check, go back to check the 4 axioms for the multiplication. Okay. So A times B equals 1. This is a given because B is the multiplicative inverse of A. So A times B equals 1. So now we can use the commutative law. This is the axiom, which is A times B equals B times A, right? Why we want to do that? Because I want to use this condition. I want to use this condition. Okay, A times B prime. But for here, A is between A and B prime, there is a B, so we interchange the position, right? We use the multiplicative, commutative axiom. Okay, so equals B times A times B prime. Then we use the associativity. B equals B times A times B prime. Right? We can put the parentheses anywhere we want. This is the axiom says. Then equal to B times, so A times B prime equals what? Equals 1. This is the assumption we have, right? A times B prime equals 1 because B prime is the multiplicative inverse of A. So this would be E times 1. So B times 1 equals B. So we proved that this B prime is equal to B. So we have no other choice. If you have another one, multiplicative inverse, we prove that another one must be the one you already have, which is B. Okay, So this is the end of the proof. So here is the one thing we should notice that right here. So let's look at some remark. So in the axiom, we use B to denote the additive multiplicative inverse of A, right? But it's not convenient because B and A just the two letters, right? It's not convenient. So here we use the one way. So we denote the multiplicative inverse of A by the following symbol, A to the -1. We use this symbol to denote the multiplicative inverse of A. So now you can see the relations, right? Okay. Then we can use in this way. Second remark. Then we can define another operation which is called the quotient or the division. Okay. So the quotient denoted by A over B. How to define this A over B? Is defined by the following way. A over B, we use the three lines. Three line equal sign means it's defined by the right side. Okay. A divided by B, or A over B means what? Means A times B inverse. So that means A over B means A multiplied by the multiplicative inverse of B. Okay. So you see, we should use the thing we already know, which is the multiplication, to introduce another operation, which is called the quotient or the division, right? So the division is not the thing we just construct already, is the thing we derived from the operation we already know, which is the multiplication. Okay. So now let's look at the next one, number 7. So now let's look at several familiar consequences, okay? Some consequences. The first one, negative of negative A is equal to A. Okay. The second one, negative A equals -1 times A. Right? We never know that, right? So far, we don't know negative A. We just know the negative A is the additive inverse of A, right? We just give a symbol, which is called the negative horizontal line and A, right? We denote this symbol by the as the additive inverse of A. That means A plus this negative A equals 0, right? So now I can say, what is negative A? Negative A is -1 times A, okay? 3. negative A times B equals negative A times B. 4. So A times B equals negative A times negative B. 5. 1 is equal to negative 1 times negative 1. Okay, so now we want to prove these 5 results. Then you can use it as you want, right? Let's prove it. So the first one. So negative of negative A equals A. So we know that if we add a negative in front of some letter, that means this one must be the additive inverse of that letter, right? So now you can see this one, this is negative. We add a negative in front of this negative A. We can treat negative A as a single letter, okay? So that means negative of negative A is the additive inverse of negative A, right? Of negative A. Do you agree with that? We just look at this number. How do we define an additive inverse? We just add a negative sign in front of that letter, right? This is the way. We have A. The additive inverse would be, for example, we use other letters. We have a number K, right? The additive inverse is just negative K. So now we have another number, negative A. So the additive inverse is just a negative A, right? So negative A is the additive inverse of A. This is just to follow the definition. Nothing special, right? However, this is the way we know that A plus negative A is equal to 0, right? This is what we know. Because negative A is the additive inverse of A, right? So in other words, A is also the additive inverse of negative A, right? Because they are the inverse of each other, right? A is the additive inverse of negative A, or negative A is the additive inverse of A, because their sum equals 0. So they are the additive inverse of each other, right? From this one, we know that, so A is the additive inverse of negative A. No problem, right? From that is just from this equation, this result. So if you have two numbers, you add together equals 0, then these two numbers are the additive inverse of each other, right? You can say negative A is the additive inverse of A. You can also say A is the additive inverse of negative A, okay? Now, you see, we have two additive inverse of negative A. One is negative A. The other one is A. So now we want to conclude that these two are the same one. Which one we should use? Which result we should use? We already have. Yeah, we only have one additive inverse, the uniqueness, right? We proved that already, right? There is only one additive inverse. By the uniqueness of additive inverse we have no other choice because there is only one additive inverse of one number. So these two must be the same, right? We have no other choice. So A must be equal to negative A. That is the result we should have, right? Number one. So we finished the proof for the first one. Okay, so we can use the similar way to prove the second one. The second one, okay. The second one is negative A equals negative 1 times A. Okay. So we know that this is the, I just write since we changed the page. Yeah, this is the second one, right? This is the second one. So the idea is the following. This is the second one we want to prove. Negative A equals negative 1 times A. Okay. So we know negative A is the additive inverse of A, right? So A plus negative A should be equal to 0. If this is true, so A plus negative 1 times A should be also equal to 0, right? If A plus negative 1 times A equals 0, so that means negative 1 times A is the additive inverse of A, right? And the negative A is also the additive inverse of A. So by the uniqueness, they must be the same. So this is the idea. The similar idea like this one, right? We have the same one, same number, but they have the different form of the additive inverse. So at last, by the uniqueness, these two forms should be the same. So this is the idea we have. So in the analysis course, you will see that sometimes the strategy for the proof are very similar for many problems. So this is the reason sometimes in the previous semesters, we always ask students to memorize some proofs. Okay, because you should, for the math course, for the advanced math course, especially for the proof, you should memorize some results or some proofs, some techniques. Then you can have some basic idea in your mind. Then when you have some new problems, you can recall maybe this strategy we can use here. Okay, so this is the reason. When you study analysis, you will see that you have a lot of things to memorize. Okay, it's not the course you already have. Okay, it's not the course you thought. You don't need to memorize anything for the math. No, it's not true. For the analysis course, for the advanced math course, so you at the beginning you must know some basic strategy for the proof. You must memorize some proofs of the result, because these proofs, the technique, the proof in the proof you will use will be applied to other problems. Okay, if you don't memorize it, you will never get a good result for the future study. Okay. Okay, so now let's look at, we use the same strategy, right? So this is the strategy we have. We want to have the two additive inverse of the same numbers, and these two must be the same. Okay, so this is the one we have. So negative 1, negative A equals, so this is the thing we want to prove right here. Negative A equals negative 1 times A. This is the thing we want to prove. Okay, so now let's add A plus negative 1 times A. Okay, A plus negative 1. We want to show that this one equals 0. If you can show that this one equals 0, that means negative 1 times A is the additive inverse of A. And we also know negative A is already the additive inverse of A. This is by the definition, right? By the notation we have. So how to show that? So we know that A is equal to 1 times A plus negative 1 times A. Right? We use the distribution axiom. It's equal to A times 1 plus negative 1. A plus 1, right? We can take the common. This is the distribution axiom we have. So 1 plus negative 1. Last time, I showed you that A minus A equals 0, right? So now 1 plus negative 1 means 1 minus 1, right? 1 minus 1 equals 0. So this would be A times 0. A times 0, we know the result we already have. A times 0 times anything equals 0. So this is equal to 0. So from this calculation, we notice that this negative 1 times A is the additive inverse of A. So, okay. On the other hand, by the definition, by the notation, we have negative A is the additive inverse of A. Right? This is notation. Why we write negative A? Because we use negative A to denote the additive inverse of A. Okay, so you can compare these two. Negative 1 times A is the additive inverse. Negative A is also the additive inverse. Then we can use by the uniqueness. By the uniqueness of additive inverse, we can conclude that negative A must be equal to negative 1 times A. The reason is there is only one additive inverse. Although you have the different form, these two forms must be the same, right? They denote the same number. So this is a negative A times negative A equals negative 1 times A. So next one, we want to prove this one. Negative A times B equals negative A times B. Okay, so we start from, this is the 3. We start from the left side, negative A times B. So we know negative A is what? Is negative 1 times A, right? Negative of something equals negative 1 times that 1, right? This is the one we already have. Yeah, negative of something equals negative 1 times that number, right? That ladder. So now our ladder becomes AB. So negative AB equals negative 1 times AB, right? We just replace this position, this box, right? Negative a box equals negative 1 times that box, right? So we have what we have. We can use the associativity right? So you can put the first two together, -1 times A, then times B. -1 times A equals the one we already have, -A, right? This is by the second result, the previous one, then to multiply by B. Yep, so we finished this proof. Okay, number 4. We can write here. Number 4 is what? We want to prove A times B equals -A times -B. Okay, so you should have some 2 negatives, right? 2 negative signs. So you can see which result we already have 2 negative signs. The first result we have 2 negative signs, right? So we may want to try using the first result to get the second and to get the fourth one, to get this one, right? Because you see here is no on the left side there is no negative sign, but on the right side there is 2 negative signs, right? So the result we have in the first one side no negative, the other one has 2 negative signs. Okay, maybe we can try this one. So it says this is so now we replace A with AB. Okay, A with AB. So that means AB equals negative of negative AB. Right? We replace the position of A with AB. So AB should be equal to negative of negative AB. There's no problem, right? This is the first result. This step is from the first result. Then we can use the third result. Negative A, the third result is this one, right? Negative AB equals negative A times B. So this would be negative A times B. Then we use we can interchange AB because this is the multiplication, right? We have the axiom to guarantee you can do that, which is B times negative A. Then we use the third result again. So you can put negative inside the first letter, right? This is 2 letters. You can put a negative inside the first letter. So you can put a negative inside the first letter. So this one would be negative B times negative A. This again use the third result. This is third result. Okay, so every step you should have some reason why you can do that, right? You should always ask yourself, not the way you want to do that. Okay, you should ask yourself if we have any tools we already proved can to proceed these steps. Okay, not the tool you generate by yourself, right? If you have some new tools, you need to prove it. Okay, you can use that tool. So since the problem is the negative A times negative B, we just interchange the position of negative A, right? Negative A times negative B. This is by the axiom. Okay. So this is the number 4. Number 5 is 1 is equal to -1. We want to prove that 1 is equal to -1 times -1. So this is the thing we want to prove. How to prove that? Since we have we already have this result, A times B equals -A times -B. So now we just take A equals B. A equals B equals 1. Okay. So we take A equals 1. and B equals 1. B equals 1 in the result 4, in this result. Then you will have 1 times 1 equals -1 times -1. And 1 times 1 equals what? Equals 1. Because 1 is the multiplicative identity, right? Okay, so this is the proof for these parts. Oh, sorry, it's too quick. Okay, so the next two things you need to prove by yourself. Okay. Number 8. This is number 8. Let me see. Sorry, the label is not good. This is 7. This is 8. Which is actually the distribution law for the subtraction. So you need to prove that A times B minus C is equal to A times B minus A times C. We have the distribution for the axiom for the addition here, right? So now you need to prove for the subtraction. The idea is you need to write this B minus C as B plus negative C. Then you can use the distribution law for the addition, right? Then you go back to the subtraction again. So this is the basic idea you will have, okay? So the hint is you write B minus C as B plus negative C. Then it's equal to A times B plus A times negative C. A times negative C, you can put a negative in front, equals negative A times C, right? This is the which result we have. Which result we have? Yeah, this result. You can put a negative in front. So you plus negative equals minus, right? So this is the idea. So this one, the next one is B, negative B minus C equals negative B plus C. So this, the first one is the general case. The second one is the special case. Why we say the second one is the special case? The reason is negative of a number equals -1 times that number, right? So you can write this one as -1 times B minus C. So then you can use this result we have. You can distribute -1 for each one, right? Then you can continue to this way. You will get this result. You need to write down, okay? Write down the steps to see what happens. The idea is you write this one, the left side, as -1 times B minus C. Then use the first result, okay? So these are the remarks for the field axiom. This is just the first axiom, okay? And we have developed many results we are very familiar with. So now you can use that result, okay? So the next one is called the positivity axiom. What is the positivity axiom? Okay, so we want to use the positivity axiom to introduce the order of the real numbers. One is greater than the other one. One is less than the other one. One is equal to the other one, right? We need to introduce using this axiom to introduce the less than, greater than, and equal. The order of the numbers, okay? So we let P be the set of positive numbers. Okay, P be the set of positive numbers. Then P is the set satisfy this P, the set P satisfies the following two results. The following. The first one, which says if A and B are positive numbers, then A times B and A plus B are also positive. So this result we will not prove because this is a part of the axiom. So we will just accept this result. Positive. The second one, if A is a real number, for any a real number, only one of the following is true. Is true. What are these the following? A is positive. Negative A is positive. A equals 0. These three choices, only one is true for any number A. So now we want to use this. This is called the positivity axiom. Okay. So the first one, if two positive numbers, the product and the addition should be, the sum should be positive. Okay. The multiplication and the addition should be positive. If you have a number, a real number, it must be positive, or negative A is positive, or A must be 0. There's only one choice. So now we want to use this theorem or this axiom to introduce the ordering of real numbers. For any AB, a real number, what is A greater than B? A greater than B, that means A minus B is positive. Okay, so here positive means greater than 0. Again, A greater than equal to B, that means A greater than B or A equal to B. So A greater than B means A minus B equal greater than 0 is positive. Okay. What is A less than B? A less than B, that means B greater than A. So in other words, B minus A is greater than 0, is positive. A less than equal to B, that means B is greater than equal to A. Okay, so we introduce these two inequalities. First, using the positivity axiom, right, which is about the positive numbers. Then we use these two to define the third one and the fourth one. A less than B means B greater than A. Okay. So now we have several properties we want to show. Properties. The first one, for any A is not equal to 0, which is a real number, then A squared is greater than 0. Any non-zero number, A, you multiply by itself, it must be greater than 0. In particular, or especially, one is greater than 0. The additive, the multiplicative identity is greater than the additive identity. Right? So let's prove it. Since A is not equal to 0, this is we know, right? This is from the condition we have. Then either A is positive or negative A is positive, right? This is by the second part of the positivity axiom. So A equals 0 is impossible because it says A is not 0, right? So you only have these two choices. A is positive or negative A is positive. Okay, so now we need to consider different cases. Suppose A is positive, what happens? Suppose negative A is positive, what happens? Okay, so case 1. A is positive. We have two cases, so we need to consider the situation for the two cases. A is positive. A is positive, we know that then A squared equals A times A. So we still denote that A squared means A times A. Two positive numbers from the first part of the axiom. If you have two positive numbers, A and B, the multiplication must be positive. So positive times positive must be positive. So it's greater than 0. This is from the first axiom in the positivity axioms. Okay. Case 2. Negative A is positive. Then we know A squared should be equal to negative A times negative A. A squared is equal to negative A times negative Y. We already proved. A squared is A times A, right? A times A equals negative A times negative A. Okay, so negative A times negative A equals A squared. So this is the result we already have, right? So you can use it. So negative A is positive. Positive times positive. We know from the axiom it must be positive. So we prove this result. A squared is positive. So we notice that there is a non-triviality axiom says the multiplicative identity is not the same as the additivity identity, right? So 1 is not equal to 0. So now we take, since this A is arbitrary number, right? So we can take A is not an arbitrary non-zero number. So we can take A equals 1. So then we have 1 is equal to 1 times 1, which is greater than 0. Right? We take A equals 1, so it should be this one, right? This case, first case. So we replace 1 with A with 1, so you will get. So 1 is greater than 0. So we finish the proof. The second result, the second property, for any positive number A, the multiplicative inverse A, which is A inverse, is also positive. Okay, so let's prove it. So we know that A times A inverse equals 1. Right? This is the definition for the multiplicative inverse. And we also know 1 is not equal to 0. Right? Then we know that one of them, either one should not be 0. Otherwise, A times B equals 0, A equals 0, or B equals 0, right? If A times B not equal to 0, A cannot be 0, and B cannot be 0. So A to the negative 1 is not 0. Now, from the positivity axiom, we know that, so A to the negative 1 is positive. Or negative A to the negative 1 is positive, right? A number is positive or its inverse, multiplicative inverse is positive. So the property asks you to prove that this A inverse is positive. So we should exclude this situation, right? So now let's see if this situation happens, what we will get. Okay, suppose. So we only have two choices, right? For the A to the negative 1. We only have these two choices. If we can exclude one choice, so the other one must be true, right? So suppose negative A to the inverse, A inverse is positive. Suppose this is the case. Then let's see if we have some contradiction. Okay. Then A times negative A inverse, which we can calculate from the property 4 or property 3. Doesn't matter which one you use. It should be the one you already have. You generally you will have this result, which is equal to negative 1. but actually you use the not property, the several identities I proved. Okay, it's equal to -1. So since A is positive, this is a given, right? Positive number A. And the negative A inverse is positive. This is the assumption, right? Then this one. So positive times positive equals -1 should be positive. Should be positive. Which contradiction to this one? 1 is positive. Okay. Because 1 is a number, right? It should be positive, or the -1 is positive, or 1 equals 0, right? But we already know 1 is not 0. This is from the non-triviativity axiom. And we also know 1 is positive. This is from the first property. So -1 is positive. It's not impossible, right? You have three choices, right? A is positive, -A is positive, or A equals 0. So now A equals 0 is impossible. A is positive. We know A is positive, so -A is positive is impossible, right? So from this one, so we have the contradiction. So this contradicts to the result that 1 is positive, or 1 is greater than 0. In other words, so the assumption is wrong. Assumption is wrong. Therefore, we have no other choice. A -1 must be positive. Okay, so we finished the proof. The third result, property. If A is greater than B, then you have the following two results. A times C greater than B times C. If C is greater than 0. And A times C is less than B times C. If C is less than 0. This is we already know, right? We multiply for the inequality. If we multiply both sides with a positive number, then it will not change the sign, right? If we multiply negative number, you have to take the opposite direction, right? So why this is true? So now we can prove it. So for the first case, let's look at if suppose C is greater than 0. Then let's look at AC. We want to prove AC is greater than BC. So what means AC is greater than BC? That means AC minus BC is greater than 0, right? It's positive. So AC minus BC. Let's look at AC minus BC. AC minus BC is equal to, we use the law we assume in your homework. This law, distribution for the subtraction. Okay. So because this is your homework, so we will use this result directly. We assume we have proved this result. So it's equal to A minus B times C. C is positive. A greater than B. That means A minus B is positive. So this is positive. This is positive. Positive times positive would be positive, right? So this one is positive. This one is positive. In other words, i.e., AC is greater than BC. Okay, so we proved the first part. The second part, if C is less than 0. Case 2. If C is less than 0. If C is negative, then that means from the positivity axiom number 2, okay, the second positivity axiom, C is less than 0. So that means negative C should be positive, right? If you have a negative C should be positive, or negative of negative C should be positive, or negative C equals 0, right? These three results. And we know negative of negative C equals C. And we know C is less than 0. So that is impossible, right? So we must have negative C must be positive. Okay, so I write here, maybe this is this. Yeah, you have 3 results. If you have a number negative C, right? You only have one choice is 2. Negative C is positive, or negative C is positive, or negative C is positive, equals 0, right? These 3 choices. So this is impossible because we already assume C is less than 0. So C is not equal to 0. So negative 3 is impossible to be 0, right? So why this is true? Because this is not true. Because negative C, we know from the several identity we have, negative C equals C, right? C is positive. No, C is negative. So this case is not true. So you only have this case. So you can see it this way. If C is less than 0, then negative C is greater than 0. Okay, so this is from the axiom, positivity axiom. Okay, so now let's look at this one. BC, we want to show that AC is less than BC. So BC minus AC should be greater than 0. Okay, it's positive. BC minus AC. BC minus AC is equal to A minus B times negative C. Okay. Of course, there is several steps, but you can figure out easily. Okay. You can take a C out, then put some negative sign, right? Then put negative inside, then you will interchange A and B, right? Okay, so you will have this one. Sorry. So this is A is greater than B. This is a given. So this is positive. Negative C we know is positive, greater than 0, so it's positive. So positive times positive is positive. Okay, positive times positive is positive. So B is AC is less than BC. Okay. So this is the first part. Of course, there's some interval notation. I believe everyone knows that. What is the parenthesis AB? That means between A and B. A, B are not included, right? If you have some brackets, that means the endpoint is included. So since this is the high-level course, so everyone should know that. Okay, so we just stop here for the first part, preliminary. Okay, Then the next class, we will start the chapter 1, section 1.1, talk about the sets. Okay. And we want to talk about the supremum of the set. Okay. Okay, so we stop here. Any questions? Any questions for the online students?
No, sir.
Okay, thank you. So I will also